welcome everyone inside the class and also remotely to the second part of our lecture 2 today. That is also the part that we changed a little bit, given basically on HD Insight and the problems. And I will use it actually a little bit here in teaching to show you also the problems sometimes with clouds that you see here. The application example that of course still exists and is quite interesting, at least that's what I got from the students as feedback often, is the violations of food quality that maybe lead to the fact of saying that basically the restaurant will fail or pass inspections. So this is a corpus or data that is basically from the city of Chicago. But again, it shows you this kind of 3 ingredients that I always say is necessary for machine learning to check before you endeavor. One is you think about a restaurant and how we operate it in the kitchen. There's a pattern of cleanliness. There's a pattern of fresh food. There's a pattern of, you think all that factors together in one way or another somehow influence the quality. If I never clean, then I quickly have some problems and maybe hygiene, then basically I will probably fail food inspections. So this would be one example of doing a binary classification. Again, right? You have seen the flowers, Iris setosa, Iris virginica. Now that's exactly the same. It's just different data. Now, instead of 2 flowers, I want to say if the food inspection will fail or pass, right? Or you stick in, and you can do this with logistic regression again, or with another linear classifier, you just put in the data. And the point is, of course, here we have data that exists from the city of Chicago that already were indicating and label that these particular restaurants with this kind of all the different, let's say, marks, food quality and freshness of the food and all the other attributes, they basically have been labeled with this guiding why that we know the label, it will pass or fail. Now, this was what we used. And if you're interested, of course, with application examples, go to our course from last year in YouTube. On lecture 2, you will see basically the second part has been changed and not anymore is addressing this particular one. However, just to shed light, why now basically this was failing and what were the problems with MS Azure, it's not that this system or this service in itself is not existing anymore. Of course, you can still have it as pay as you go, right? You basically swipe the credit card and you can have a HD Insight Spark cluster in the cloud that is humongous. The problem is that we have here in the course, we are bound to educational status. So I had to always have basically a so-called student subscription in Microsoft Azure. And we will use it also for other things in the course later, right? Not anymore here for machine learning. It was very convenient, I have to say. It was a good way to learn Spark workers, Spark head nodes, something which is not obvious to you, but we see how that materializes when we have the complementary lecture 3, where we then look really on Spark behind the scene. But essentially, it doesn't matter so much. We now move to another cloud. But of course, that's something where the modus operandi, how you do this kind of 7 steps that are provided here as an example to do cloud computing in a stepwise approach that we do now for many years, also based on student feedback. It's the same idea. You here and there change a couple of things, and I will make the point of it. In previous times, of course, you look for the subscription of students in MS Azure. That was one of the first steps. Then you want to deploy a Spark cluster, right? Something in the cloud, which is often used for parallel computing. You use their so-called template prepared and can steer the number of worker threads and head nodes, things we will talk about later in the lecture 3. You have started then up your Jupyter notebook and using then the PySpark environment from Apache Spark. And this really makes it the HD Insight package. So there are lots of Hadoop, Apache projects, Zookeeper, many different, let's say, open source tools bound together in Azure. But the good news is they are also available in Google. They're available also in Amazon and so forth. So that's why we switched to Google, for example, because it's also existing there. You create a so-called Spark session we will talk about in examples. And then basically, of course, the first thing you do as machine learner is you check your application data set. You want to understand it. You want to prepare it for your modeling. So feature selection or feature engineering even. So you look a little bit like we did with the flowers. So which attribute could actually work here, which is basically now something which could differentiate the flower. So of course, then you start the modeling as we have done the perceptron. Now we make the move to logistic regression. So we use this logistic function or sigmoid, but then you perform your machine learning on this cluster in the cloud, in this Spark cluster, which is actually very scalable. And on the scalable notion, we will talk about basically when we have lecture 3 much more than today, because today we focus a bit on using the machine learning now, before we look basically what now Spark can do in terms of operating in the cloud. And of course, machine learning always ends with some evaluation, fine-tuning, refinement, hyperparameter tuning, lots of these things where you can have lots of different measures, error measures looked at. This is, of course, something which in a way never ends. Just basically now think about that this is still there. If you want, lecture 2, lecture 3 is all on YouTube. You can look at it, lecture 2 explicitly. But of course, this also changes our assignment to a new application problem, which is now bank deposit. So here we talk about essentially a marketing campaign of a bank, always phoning customers and would say who want to make a term deposit again or not. And in order to predict this, essentially, we have here again a binary classification task of saying, when I go through all these different characters and I have lots of data available actually from Kaggle. Who knows Kaggle by chance? It's a competition/data set repository, also online, open, that you can actually download. So this data exists. We know there's not really a formula. You cannot really in the moment say, well, just because he is a manager in 50 years of age, he probably makes a deposit, but the musician in the 20s doesn't, although he maybe had a very good title out and has lots of money to deposit. So in a way, we're searching for something in the persons now, from the character, from the education, from lots of different factors. What would be this line, right? Which would be separating again. Here it's not so easy because we see already a person is not linear, it's not simple, right? This is something what we already can imagine probably. That's why we call this basically catching non-linearities in the person, because we are all, let's say, very different and we need something which is a bit more smarter than just the perceptron we have seen, coming then later to this logistic regression. So essentially we have, again, this kind of 3 ingredients, which now saying, okay, we can go for machine learning, perfect. Now we would have used this maybe on HD Insight if it would be available for the education, but it isn't. So what we will do now is essentially use the so-called Google Colab cloud. You say it's, of course, sometimes slow. It actually depends also which resources you get. It's never really fixed necessarily. You sometimes get just really arbitrary resources. But this is a cloud that now everybody can access, and something where we at least can start with using Apache Spark underneath. And the way how it operates now, you see a little bit the 7 steps. Again, it's very similar, the material, than we have seen in the HD Insight. Now, the first step, of course, you can do a subscription if you want on Google Colab, I think $9 or so per month. Then you basically have a very much better stable environment to get resources, but it's not required, right? Also not for the course. The only thing that is required for the course is to have a Google account. And of course, you can approach me later on if you don't want to create a Google account, but today it's very hard almost to survive in the world if you don't have a Google account, but there might be these cases. Then the second we use is basically a Spark cluster in the Google Cloud. And this now is the interesting thing of this other technology layer. No matter what cloud it is, in Amazon or Google, we have a Spark cluster usually available because it's one of the key technologies in cloud. That's why we cover it in the course. The other element you already know also from my, let's say, earlier demonstrations with Jupyter. Of course, now we're interested of not doing it in Anaconda somewhere on our laptop, but inside the cloud, as we have done basically with the JTC in Germany, right? The German cloud. So remote access Google Colab in order to use then this interesting Apache Spark for machine learning algorithms. So the steps are actually almost the same then from there on. Once I have settled this, I know PySpark is available in the Google Colab. I can literally use again the same steps, basically sometimes even the same code to really, port basically your code from one cloud to another. This is not always true. There's some, let's say, small hidden assets sometimes. For instance, how you access the data in Amazon is a bit different, for instance. But essentially what you see here then in the final steps, this is essentially the same idea how we would have done in HD Insight the process. Now let's come a little bit to more detail, because this is, let's say, a very high level view of how to use the clouds. The step first now, when we go through all the 7 steps, which you also will do in the assignment as a walkthrough, so to speak, also with then a different, let's say, data idea and a little bit a different data question also, but also a replay of this is one part of the assignment. So of course you have to do a kind of Google account, as I said earlier, to use Google Colab. But as you see, the look and feel is very like notebooks, basically. So who has used Google Colab before? Oh, very many people, very good, yeah. So in this sense, many of you know the game already. It's a look and feel of Jupyter, but in the cloud. There are no costs essentially to it. And I will also demonstrate this in one of our practical lectures very soon, just how to use it. And, you know, then you basically quickly come around how that works. Here's one example. When we now think about installing the cluster, there are many different ways how you can install a Spark cluster in the cloud, especially in Google Colab. Here's one way of doing it, where I say it's really a basic thing, so that you also learn a little bit about Unix, that you learn a little bit about starting from zero, right? So this is something where you see we basically have the OpenJDK. So we talked about this. So download one specific version of Java for which the tools are for. And basically, when you have this kind of exclamation mark there on the top, apt get install means it's a Unix command you kind of execute through Python, more or less, right? And this will be then installing, first downloading and installing this particular JDK version. And then you see with wget, we're downloading specific versions of Spark. That's also very important because there are many different versions around, and your code is often tuned to one or specific version. So it will not work because, of course, the code always will be, you know, modernized, new classifiers are in, and so forth. Then we do this ls-al. It's nothing like Linux of saying what files are existing, right? So you learn a little bit Unix. It's really low level into the cloud, so to speak. You tar, basically untar it, that we have downloaded the package Spark. And of course, here it's important that you have basically also the right version numbers in these packages, in this target. Once you untar it, you have, let's say, a directory which has all the Spark and Hadoop in it. And then you can basically, you know, do some preparation here just for some environment variables as an example, how you really can start from scratch, so to speak, with Spark, right? So, of course, you don't know really about Spark and all the details. We need a whole lecture 3 that provides you all the details. Here, I will always come back. And we'll do now the logistic regression with you step by step, the data science question. And then in lecture 3, we will learn basically how Spark really deals with this, with RDDs, with pipelines, and so forth. But putting all in one lecture is a bit too much to understanding this. And on the other hand, of course, clouds are extremely complex. They do lots of stuff together, parallel computing, data science. That's why we basically have here, a kind of stepwise approach where really complementary lecture 3 will then look much more deeper inside. As an example, when we get to Kaggle and we want to download this data set, there's a CSV, a comma separated file from all the data from the bank, from all the basically previous customers that had done a deposit or not, with all the different features. It's in a so-called bank CSV that will be also available to you in the basically assignment. And then you basically can use different ways now to upload it. My suggestion is always use drag and drop. That works. My experience working with Colab a long time is somehow this file upload doesn't work for me sometimes. I have not directly a reason why, maybe firewall settings of your local computer or depending on which system you are. But this is something what you can then upload to the space of the cloud. And you can see in the URI on the top in Colab Research Google.com, although you're locally doing it with your laptop, you're already accessing the cloud on the other side, somewhere in basically in US hosted, and we don't know where, which is of course one of the key ideas of cloud computing. So once you basically uploaded the data, the idea is now to start a PySpark session. If you remember, one of the steps was now to have this PySpark link to the Spark package to use it from Python. Here's one way of doing it by pip install, a so-called find Spark package, which helps us a little bit of doing, an easy link to basically the environment we have of basically getting Spark connected to our PySpark session. And then we just started. From that moment, and you will see that takes a bit time when you do the Spark session builder, you're basically getting access to a Spark cluster underneath the hood, right? Somewhere in the cloud in this Google Colab. And the details there we will allude to in lecture 3 and in practical lecture 3.1 and so forth. But the key message to take away is that everything is underneath the hood, and you just program Python, but using the machine learning libraries from Python and from Spark, right? So that is, of course, an idea. When you now start off using scikit-learn, something from Anaconda in the cloud, it will be also not really put on the Spark cluster. So that's why always when we do something, it will be connected to this PySpark or to the Spark session, really. That's an important part of it. No one prevents you from using scikit-learn, which is a, let's say, serial package on the cloud, but it will be, of course, still having the similar limitations like working on your laptop. Now, when you have step 4 now, creating the Spark session and so on, the first thing what we did was also wanted to do in this case is check the application data set. So this is always where, you know, data analysts, data science experts, they always start with this. We had to do a data inspection, data understanding, and we have said these are all different personalities. They have all different, let's say, attributes like the flower, petal, sepal width, and so on. They have, of course, educational status. They have housing, a loan they had maybe in the future. Of course, if they're married, not married, the job, whatever. So they have all these different items, and we see already there's a nice view. Someone from you used pandas. I think many used Python. Yeah, pandas already. So this is a bit more beautiful to work with data. That's why it's often used and a bit more easier. Of course, you can do the same with data frames. And for instance, here you see an example with the schemas, which are essentially saying similar elements. And with pandas, it's a very nice Python package to, you know, flip around and have nice visualizations. You see here, we take the first 5 of the data set, right, from all these different people. And then we see a little bit an example from, you know, what does it mean? It's also important to understand one thing, which will be important for us when we're modeling. What are categorical attributes and what are numerical attributes? Or basically categorical is something like married, unmarried, yes, no, things like that. But numeric values is things like the age and, you know, basically the balance they have on their bank account and things like that. This will be later on a bit more important for us when we do the modeling, but at least it captures already the understanding. From the scientific question now, or the data science question, of course, we want to find, you know, again, the line, so to speak, that differentiates now basically those that don't do deposits, when I call them, in the bank, or basically those that do deposits in the bank. And of course, I don't want to do this for them because it was happening in the past. The point why I'm doing is that when I call certain people, I want a priority list where I already would know there's a very highly likely probability that this scientist here, this fellow, will actually do a deposit, right? And I think we have a pattern. We would say maybe it's like the physician here, but on the other hand, we also know there are many rich musicians, rich managers that would also do a deposit, but didn't. So in a way, we need an automatization for this process. Someone who is looking on all this as a human in the phone box and says, okay, I know these all, but to know exactly which of the people to first call is a very tough question, even for a human, right? To put all the factors in. And of course, not forgetting that you have sometimes thousands or millions of previous customers to look through. And exactly this is where machine learning now can help. It gives you a quick recommender. These are the top 5 priorities to call this afternoon. They're very likely to put the deposit. And of course, every day a deposit really matters a lot in terms of, you know, revenues to the bank. So now another element when we talk about machine learning is the so-called class imbalance, which is important. I would have normally a complete lecture about it, but simplified a little bit means that when you do classification and you want to learn from previous, you know, samples from these classes, you don't want to have just 2 class samples from this part and just, let's say, millions from the other, right? Then you would have a bias of learning a little bit how much to be like one class. So what really important for machine learning is, and sometimes a challenge, in fact, for real practical data, is to have a relatively balanced class setup. And you see that here. So the deposit that the people said no, all those that said yes is relatively the same. It's all in the 5,000s to 6,000s. Exact, of course, it doesn't have to be. It's all a statistical approach. And also the technique is with optimization, let's say something which is a little bit, you know, not exact anyhow, but it is much better than having, let's say, 10 with a deposit and 1 million without a deposit. Then basically machine learning system I will learn will be completely biased and unusable really for practice. That's an important consideration called class balance. And there's several techniques how you can then subsample from an existing distribution that I left out a little bit here, but of course, which is very relevant in practice. What is often used is some summary statistics. So people look then again on these fields. It gives you a little bit, okay, I have people from age 18 to 95. You can imagine a relatively simple element. Maybe the balance would be important. So there's actually some people with a big minus balance. Maybe that I don't want to call, but those which have 81, thousands in the bank account. So maybe there's a relationship which is also very important to consider. On the other hand, then you think day. This is something which is very strange. So of course we know there's maybe a month and day, but it really doesn't reflect something in the data. So maybe I also can subsample out of the data some of the attributes that don't matter, because the more attributes I have, the more machine learning processing I need. Hence, you look also on some, let's say, feature reduction, feature selection in terms of attributes which really matter here, right? So this is one example of performing this data understanding part. In this case, just a normal day in the week is no really dependency basically for this. Hence, we get rid of day and month as an example out of the data set. You just remove this. This is basically now called feature selection. You select those which are not month and day and come to the new, let's say, overview where you just select, let's say, those. And you have again the new schema, which is, of course, then without day and month. So it's also typical machine learning process. And you play around sometimes with this. You maybe would remove some others also of that where you think, it's maybe not really needed. But on the other hand, that's something, of course, where you have to be careful not to have the most important things removed, because then maybe your classifier cannot learn at all the pattern. One example might be the balance we have seen. This might be a big impact to keep that. So when we have done this feature selection, I said to you earlier, we had done the data inspection and looked in this, and you'll notice that we always use PySpark, right? Just as a side remark, that we really work with Spark libraries here. In this idea, we have now to think about that. Firstly, we have categorical items, which are somehow very, very strange to consider in mathematical models. So for mathematical convenience, we have to transform them, so to speak, in a more mathematical convenient way, which you have here as these kind of warning signals, right? You see here that we have categorical items, again, yes, no, and so on. And basic or management, education was another. And then those which are more numeric, so values really. And essentially what this little thing is doing is we create one compact vector of information out of the data. That is a key goal that we want to do, but we want to use categorical data, which you cannot use because it's just text and strings. And then we want to have the numerical data, and we want to put all in one clear feature vector, which is then for our logistic regression mathematical convenient to put in. So in a way, I'm reusing, you see a lot of these fields in the beginning, all the categorical ones, and I use a so-called indexer and then a one-hot encoder to make this as a mathematical representation, which of those, let's say, educations and so on, are done in the different columns. So when I have done this indexer and this encoder, I have a big list. That's why it's a for loop. We go through all these different columns, basically, that are in this categorical field, and have a very long list of this hot encoding. Now, when I do then basically the label, this is something which we already know, the deposit, that was a yes and no. But of course, this is not just categorical. It is also our key idea of learning from. This is our why, right? Our guiding label why. Did deposit, did not deposit in the past. So we have to handle this very different, basically inside the logistic modeling. As we have seen with the flower, the why was never in the model. It was just at the end to check if I learned well. You remember, right? We always had all the x's, our data, summed up linearly using weights. That makes it a linear model. And then I had an output. Once I have the output, I check with the label. The same here, we don't want to put this inside the model directly, basically into the feature vector and the attributes of the flower as we had. Here we keep it separately, but we make it more convenient on basically just naming it label. Now putting all of them, basically the remaining columns and all the remaining information together is this interesting assembler. So the details of that is basically not so important to understand, but the key idea is really to have this interesting, let's say, class vector that we generated from this hot encoding, plus, of course, then all our numerical ones, because they are also, of course, important key information. But here the beauty is it's mathematical understandable, right? I have a certain age, I have a certain balance. And I put this all together, let's say, as a new vector, which is called features. And now essentially I can, ignore a little bit whatever else is in the data set, right? Because now I have that label, which is essentially our Y we had before. And like sepal width, sepal length, and so on from the flowers, we have now exactly this features vector existing. Let's look at this. Python can do this very nicely, as you know. And let's look a little bit behind the scene, how that looks like. You again have now, of course, all the different elements here from the data frame, and we have said all what is now in this one vector captures now the essence of these different personalities with balance, education, and so on. So what's really new is now is literally you have in this data set now these two first new elements, whereby we have to say that actually the first one is not really new, it's the deposit, right? We just create a new one based on that to call it, it's a little bit more easier to understand it. Sometimes what we often do in machine learning to understand the code quicker, because here everybody knows from machine learning directly what a label is. So if there's a label as a kind of indicator, it helps people for the readability of the code enormously. When it's just deposit, they have to understand the application domain question first. And of course, then the feature vector that I said is now a very compact representation. In Spark, we will do something called pipelines. That's not obvious to you. We see how that materializes in lecture 3, right? These are Spark pipelines to reproduce also certain data science elements again and again. And there are different ways how you transform it and how you fit it essentially to a Spark cluster. And yeah, by doing so, you're using Spark all the time, essentially without really knowing that you do something very, let's say, specific and parallel and scalable, right? Because now the code looks almost like you use Anaconda like we have done in 1 hour practical lecture 01. And now essentially you could have, of course, from the initial data analysis, more views into the data, just understand it well. But you will also want to start the modeling at some point in time. And of course, for the modeling now, it's important to realize what's really happening in the first 2 rows here, because now we switch a little bit to the modeling perspective. We want now something to create a machine learning model that takes as input the features, which is this compact representation we just created. And as output should be always, basically looking and checking the label. Right? So these two are very important to us. That's why we kind of focus on this a little bit. And of course, still they represent in this feature vector all the different data that we had here. It's just more compactor so that the mathematical model can work. Also, we discussed in the first part of the lecture that somehow when we do machine learning, we always need to have a training set and a test set. So we have to basically cut this away from each other. You see here is a random split between the data set that we have in a 70 to 30% rule. That's also not obvious. So basically there's no quick rule that just said you have to always do it like this. But that's one example how you can start from. And then you see the counting of the data set there in the code, where we have now more training samples to train from. And then we use a classification from the ML package of Spark to do, logistic regression. These are all classes existing in Python. You can nicely reuse them. And you see directly the features columns we put in are our features. So our feature vector with the compact representation. The label that we put in is the label that we generated out of the deposit. And you see an iteration because we're using now an iterative algorithm to come to the solutions. We will see in a minute. And then basically fit to the train data, right? So the test data we have thrown away in the corner, we don't look at. So it's basically remaining there to see. You will also see, and that's why the HPC machine is here, that the fitting takes time. Now it's where actually the machine learns really, where the learning takes place again and again from the data set going through all the different samples in the training. and does something. And of course, the fitting is now loaded because it depends on which of the algorithms you choose, which model you use. Logistic regression uses something called stochastic gradient descent, which we will look at in a moment. You also see we can, look at the beta coefficients. There are lots of different ways how you can check the training. Does it get better? Is there a possibility of, precision recall? Is there a possibility of, you train under the area, under the RAC curve? They're all different ways of, let's say, if the model really learned, you can have accuracy. So all of them here in Python to list would be very long and cumbersome. So I had a couple of few that is derived from a training that is basically existing. And we see that essentially when we look further in this, that the idea of really doing this comes back to the ideas we had in the beginning. So now the question is just we're breaking off this PySpark that you have seen, model fit. Yeah, so the real logistic regression fitting. So what does it mean when I fit? So in the end, you basically have seen already in the first part of the lecture, very simply, we had this linear classification where we really did an abrupt way with a sine function. We put the signal through, always W transpose X again and again and again with the perceptron learning algorithm. And we have seen over time it converges, and then we could say -1 or 1 because we put it through the sine function. In fact, when you don't use any function, you have a typical regression. So then you have a real valued output. That's what a vector transpose vector becomes. It's a real valued. And then you can actually plot, as you see, the trend or whatever your application domain question is. That is what we call linear regression. Then linear classification took us to this idea of using the perceptron. Still, the same idea applies in logistic regression. We take the same model characteristic, right, with all the perceptron idea. The only thing that changed is instead of using this very abrupt sine function, we use now the logistic function, which is like an S lying really smooth. That's why it's also called sigmoid. You see that a little bit here. So this is essentially nothing else that you see. Again, we put the same signal through, but here we use this so-called sigmoid function, which is defined like this. And the beauty is it actually gives us a probability between 0 and 1. So it squashes all the values that come always between 0 and 1, but not like +1 and -1 so hard as we have seen, right? It gives you, of course, on the line somewhere an element, which also shows, is it more a tendance to 1 or 0? This is something which we previously not really had. That's why it's a bit so-called a soft threshold. We understand better what's happening and can talk about probabilities. Now, by also doing this, we can actually now optimize. We're having essentially this line we put all the way through. And again, as we did with the perceptron learning algorithm of just adding or subtracting the vector, here we define the error measure, which is actually nothing else than a pointwise error measure. We can reuse here because our label Y is still there, right? So every time, basically, I have one signal of those coming through this, I can actually check with my weights I just trained with the X, which is constant. This is our data set. And then the guiding label Y, if it's actually true. And the error that we get out of this, depending on the different weights that we will have, this is, of course, something we want to minimize when we learn. So this should be something going down, right? And who knows what we do when there should be something going down in error measures? Optimization. Someone has used optimization. SGD, maybe, stochastic gradient descents. Okay, so this is something which we put in the pool box on the table and say, okay, optimization mechanisms, that's what machine learning is built on. Basically, all the heart of machine learning is optimization, where you basically minimize an error. And here we can do this beautifully because we have these labels that actually guide our process. How that works is so-called stochastic gradient descent. It's a very, very famous one. Also sometimes gradient descent or batch descent, depending on how many data items you take. If you take gradient descent, you have to take literally every little data item, basically, and stochastic gradient descent just puts a probability to it and samples out of all your data and try to reduce the error measures. What's today actually mostly uses kind of batch descent. You give a batch size of data points and then essentially those will be taken into account before there's an update on the weights. But there are different manipulations, there are different optimizations to it. All of them have in common that you have now this error measure that you try to minimize. And in order to understand where you are in terms of, getting better or worse, you can take the derivative, which is essentially saying here on the right-hand side, then that you basically look on the next step in the so-called learning rate step, where you basically are in the next steps taking the derivative. This learning rate is something which we call a meta hyperparameter that you can actually steer and will have, of course, important impacts, as I show you in a video in a moment. And there are many different ways how you can describe this. All of them have in common that essentially it will determine whether you go basically lower, if basically the number is positive or negative in this derivative. And then, of course, you update this depending on going negative. Now, of course, it will give you the ascent, right? The derivative. So that's why we take the minus to take essentially the descent, the opposite way of the ascent from it. The simplest way how you can realize it is usually this kind of going downhill. And you integrate this now with the error measure in this interesting algorithm you see there, logistic regression. Of course, normally it would be a wholly complete university lecture that I have now more or less in one slide or two, just to give the basic principle. But you iterate now the way again and again through the data. As we said, you have the error measure defined on the previous slide that you always can have in the delta and update the weights. Now, if you do this and minimize the error over time, you will see that your machine learning model gets better. And that's, of course, the goal, what we want to do. And of course, you specify the number of iterations, right? This is very important. You have seen max eta 10 was what we did in order to say how long we learn and how long we want to do this. So here's the idea of the, basically of the stochastic descent just in a very short video. You see here. Where essentially you have this S-shaped curve, and a little bit hard to see with the light is maybe here the green dot, right? It wanders downhill. And maybe there's a YouTube link where you can see the video and so on. It's indeed in this classroom not so visible. Hopefully it's online better. We can do this. Oh. But yes, there are also a couple of other examples that you maybe, when you want to look at these slides again and at this YouTube video, which shows you then that by basically doing this downhill, minimizing the error measure, you go downhill, as we said in the right graphic. And there are different ways, how many learning rates you can steer, how much steps, how quickly you go downhill. These are all optimization elements, which we don't cover right now. We will look at this a little bit more when we come to neural networks. Right, and at the end, we have some logistic regression model evaluation. We will have, let's say, very different ideas how you can do this. We look at so-called true positive, false positives that you see nice. So these are within our samples, but of course there are many false negatives and basically also true negatives. This is a really complicated topic. That's why I bring you again an explanation on this. From those you can derive things like precision or recall, things we also will have in the practical lecture a little bit more explored. I think it will be adding to too much complexity now to get too much in details. But these are measures where you can see the area under the ROC curve. It should be quite big to really have a good, let's say, model performance. And there's lots of Python training summary that you can actually use. On all these iterations, there's some, let's say, interesting elements that you can derive from, not only the maybe false positive rate, true positive rates, and so forth. You can have different characteristics. You take the F measure, as it is called, as one example. And then you come, of course, in the end to something when you see and really want to use it on the test set. So now we take the one that we thrown away from the corner back to real data in the future that we have never seen in training and want to predict. And then I see the prediction of the different classes, who will be a deposit, who will be not a deposit. We saw the raw prediction we put basically in the logistic function and also some probability to it. But here's important now that we use a test set, right? Not the training set. This gives us the predictions, which are very important. That actually answers us now also the question, this new customer, what would he be? We just put it into this with all the different characters, and then essentially we know exactly, or to a certain probability, actually how good he is. And you see here the area under the ROC curve is 88 already. So it's quite a good performance of the model. There are evaluators we will talk about also in Spark and so forth. So that's definitely something we will look in the next lecture. Finally, just some cross-validation idea where you can basically tune your model. Of course, now significantly, you can check for biases in the data. For instance, if you take decisions on the training data is already contaminated, so you should not use it for training. So this is, of course, strange. So you would usually use a validation set to perform the model decision. But also for validation, usually I need 2 or 3 lectures in university lectures to explain the whole concept. But here, there are lots of ideas how you can really tune your model, how you can be sure that what you report outside the world is really, let's say, correct. Good. So, and in a way, we will come back again and again to this in lecture 3, in lecture 3.1 in the assignment. Just maybe as a summary, a 1-minute video about Amazon, just to show you that, of course, there's also other machine learning in the clouds possible. It's a YouTube video, so those that want to leave, it's okay, no problem. Others, maybe I just played here for the YouTube recording.
Traditional machine learning development is a complex, iterative process. Amazon SageMaker Studio solves this challenge by providing all the tools needed to build, train, and deploy models. Let's see how it comes together with an easy-to-follow example. We're going to create a machine learning model to predict the cost of homes in the US. The model uses historical housing price data, number of rooms, and mortgage rates to predict sale prices. All this data can be put into a CSV file and then dropped into an Amazon S3 bucket. With just a few clicks, you can launch Amazon SageMaker Autopilot and spin up models with different algorithms, datasets, and parameters. Autopilot iteratively trains dozens of models at once and then puts the best sets on a leaderboard ranked by accuracy. You can dive into any of these individual models and inspect their features, and then deploy the best one for your use case with a single click. After deployment, you can oversee model quality using Amazon SageMaker Model Monitor. At any point, if problems are detected, you will receive an alert so you can retrain the model as needed. With Amazon SageMaker Studio, you can pull the tools used in traditional software development, such as debuggers and profilers, into a single pane of glass to build, train, and deploy machine learning models at scale. Get started today.
Okay, here just a disclaimer that I'm of course not paid by Amazon, but it's an interesting service. It automates a lot.
Traditional machine learning
pipelines, so to speak. That's all for today, and we continue essentially with lecture 3 then on Thursday. Thank you very much.